Hello, I'm Cole Synergy.
And I'm Dylan Sinan.
We're from Section 4, and today we're going over Lab 10.
All we're really doing here is first setting up by calibrating a ruler with respect to a microscope. We use that calibration factor, which we measure by measuring, the distance along the ruler with respect to how many pixels there are on your sensor to calibrate that. From then you can measure distances of objects such as the emitting area from an LED. So we measure the areas of a white light LED that way. Here we have a laser shooting into the microscope, the cavity we measured, the green, blue, and red LEDs, their calibration factors, the emission areas, and a reasonable mode spacing.
As part of the experiment, we were tasked with finding the emission spectrums of an LED and laser diode source. The way how we were able to do that was using this optical spectrum analyzer for the laser diode, and then using this emission spectrometer for the LED. And then we have this computer that has all the softwares for both of them, and we would run the software. And so when you do that for the LED, it's a clean emission spectrum. You'll get one peak. When you do that with the laser diode and the optical spectrum analyzer, you'll find that there are multiple modes. And with your laser diode, you can also calculate your mode spacing, and you can do that using features in your software. And then you also just want to find your peaks of wavelengths. And that's For the results, we have our emission spectrum of the LED, which shows the highest peak around 626.5 nanometers. And for the laser diode, we have three graphs at different thresholds showing the lasing process and also the mode spacing calculation, which was slightly different than Part A's. For Part C setup, we hooked the function generator to the source in oscilloscope and set it to square wave. The detector captures the square wave signals from the source, and we measure the output voltage using the peak-to-peak function and rotate the source, then plot the data for both LED and laser diode.
As you can see here, we have a fairly Lambertian LED. Then we can see that we have a pretty unpolarized LED, which is to be expected. Then we have our data for a major and minor axis of our laser diode showing that it is elliptical. And then we have our polarization ratio for our LED that shows that it is polarized and that it has a very small signal and a very big signal. The small signal could have been smaller, but the lights were on. A LED power by using this voltage source wired in series with this multimeter measuring current. The output power is measured by this laser diode. We're going to be using this to measure the input current. And
For Part D results, we have graphs for input current versus optical power. For the LED graph, it is linear, while the laser diode plot becomes linear for input current more than 20 milliamps.